Hello students, today we will discuss about the topic Friis transmission formula and link budget and link margin. So this topic is very much important to calculate the received power of a receiver antenna systems, and also the link budget and link margin is to estimate what will be the power received by the receiving antenna. So this is very important topic in any kind of wireless communication link. Right. So first we will discuss about Friis transmission formula and how to calculate the received power with the help of this Friis transmission formula. So this is nothing but accounting of power gain and losses of any communication link if it is established between two antenna systems. The one is transmitting antenna part, and this is the transmitter part, and this is the receiver part, and these two antennas are separated by the distance r, where AET is nothing but the effective aperture of the transmitting antenna, that is the open end, the area over which the antenna will receive or extract the power. But AER is nothing but the effective aperture of the receiving antenna systems, right? And these two antennas are separated by the distance r. Now in this case we are going to calculate what is the power density. So power density will be calculated by knowing the transmitting power as well as the gain of the transmitting antenna. So PD is equal to PT GT by 4 pi r squared, where r is the distance between the element. If the r is longer, then power density will be less. So power density and distance between the antenna is inversely proportional, right? So for calculating this power density, we should know the gain of the transmitting antenna systems in this case, as well as how much power the transmitting antenna can deliver, right? So here and the power density will be calculated in this way, and the received power will be calculated by taking this power density multiplied with what is the effective aperture of the antenna. So based on the antenna dimensions or opening end, the power reception will be different, right? So the effective aperture is nothing but it depends the size of the antenna systems. It may be linear antenna, or it may be parabolic reflector, or it may be horn antenna systems or loop antenna systems. For different kind of antennas, the aperture will be different. So aperture is mainly for based on the dimension of the antenna. So according to the dimensions, the power reception will be different. Then the gain can be measured by taking this formula 4 pi effective aperture by lambda squared. So these are the relations of received power as well as gain with respect to effective aperture. Then this is the Friis transmission formula, that is the power reception can be calculated by taking PT is the transmitting power of the transmitter, and GT is the gain of the transmitting antenna, GR is the gain of the receiving antenna, multiplied with lambda by 4 pi r whole square. So lambda is the wavelength of the operating frequency, right? Now we will discuss about how to derive this Friis transmission formula by taking this power density relations, right? So the power density at receiving antenna can be calculated by P is equal to PT by A, right? So PT is nothing but transmitted power, A is area. So here then the power density P of the plane wave incident on the received antenna distance r from the transmitting antenna is given by the power density is equal to what is the transmitting power by 4 pi r squared. And in this case, if the transmit antenna has an antenna gain, so GT will be combined with this power density. So we can directly multiply the power density calculation for GT is multiplied along with this power density, right? So GT is the gain of the transmitting antenna systems. So assume now that the power received antenna has an effective aperture given by AER. So we can calculate the received power can be multiplied with what is the power density we have calculated, multiplied with the effective aperture. That already in the previous slide we know, we discussed about these relations. So received power also depends the effective aperture of the receiving antenna systems. So by calculating all these terms, so we have power density formula over here, substitute in this received power, so we can expand this relation PR is equal to PT by 4 pi r squared GT into AER. So up to GT, this is the power density of the antenna systems. Since the effective aperture for any antenna and also be expressed by AE is equal to lambda squared by 4 pi into the gain. So this is the general formula for effective aperture. So here we are going to derive the Friis transmission formula. For that we need to take transmitting antenna, gain of the transmitting antenna is equal to 4 pi AET by lambda squared, whereas AET is nothing but effective aperture of the transmitting antenna. So this formula already we know, right? So this is the relation between gain of the antenna as well as effective aperture. So now we have to substitute this GT value over here in this formula of PR. Then PR can be expanded, this PT is PT multiplied with 4 pi AET by 4 pi R square lambda squared into AER. So here 4 pi terms will be cancelled, remaining we have GR is equal to 4 pi AER by lambda square. Similarly, we have to calculate the same way for taking this gain of the receiver. So now the resulting received power can be written as PR is equal to PT GT GR lambda squared by 4 pi R squared. So GR, we know the value of GR is over here. So substitute all these relations over in this case, then we will calculate this formula, right? So from this AER, so from this gain of receiving antenna, we are going to calculate what is AER, and we have to substitute over here in these relations, then we can calculate what is the received power. So after that, lambda can be replaced in terms of C by F, then this is the relation for that. So now this is the final relation of received power. Using this Friis transmission formula, it is used to find out the received power of any communication systems. So if the antenna are not polarization matched, the above received power could be multiplied with the polarization loss factor. So polarization loss factor is used to find out what is the degree of mismatching the orientation of transmitter as well as receiver part. So now this received power can be calculated by taking loss factor multiplied with this remaining terms. So this is the Friis transmission formula for any cases. Now we will take one example for calculating the power density. So in this example, GSM 1800 cell tower antenna is transmitting 20 watt of power in the frequency range of 1840 to 1845 megahertz. The gain of the antenna is 17 dB. Find the power density at a distance of first 50 meter and another distance is given as 300 meters in the direction of maximum radiations. So here they have given GSM tower, it is transmitting 20 watts of power with two frequency ranges. It is the band 1840 to 1845 megahertz. The gain of the antenna is 17 dB. So we have to calculate what is the power density. If the distance between the transmitter receiver is 50 meters, what will be the power density? If the distance is 300 meters, what is the power density? That we have to calculate it, right? So we know the power density formula, that is PD is equal to transmitting power and gain of transmitter antenna divided by 4 pi R square. So unit is watts per meter square. So now first we have to calculate gain, the given gain in dB for the linear value. So we have to convert dB to linear scale. So we have for 17 dB, if we convert in linear, it will be 50. And then we have this is the formula for calculating the given dB into linear scale. Now first case we have to calculate for distance is equal to 50 meters. So substitute distance equal to 50 meters, that is in R, and this 50 is the gain in linear scale. This 50 squared is the distance between the transmitter to the receiver. So now we have the power density is 31.8 milliwatts per meter squared, and if the distance is increases, that is about 300 meter, and the power is reduced from 31.8 milliwatts per meter squared to 0.88 milliwatts per meter squared. So power density is reduced, right? From this we can understand. So if the distance is increases and the power density will be reduced, so it is inversely proportional, right? So now we will move on to this link margin. It is shortly named as LKM. What do you mean by link margin? In a wireless communication system, the link margin is the difference between the minimum expected power received and the receiver sensitivity. So it is the difference between receiver sensitivity to this, what is the power received from the receiving antenna systems. So that is called as link margin. So the difference between sensitivity of the receiver to the power reception of the receiver. right? So for example, if the sensitivity is fixed about 10 dB for any system, any receiver, if it is fixed about 10 dB, then the received power should be greater than or equal to this 10 dB values. Otherwise, the receiver does not work, right? So that is the minimum sensitivity we have fixed about 10 dB. So the receiver has to receive the power at least minimum 10 dB range. So minimum 10 dB to maximum value. So that difference is called as link margin. So it is very important calculations. The receiver sensitivity represents the received power at which the receiver will stop working. So this is another way we can define what is the meaning of receiver sensitivity, right? So if your received power is less than 10 dB, what will happen? The receiver does not respond anything, right? So the negative value of link margin, the receiver does not work anything for this, right? So this will be indicated with respect to dB. So for example, this is a wireless communication link we have. So for this link, this is the transmitter part. This is the complete transmitter part. We have a transmitter radio and we have a transmitting antenna. In between a cable is there. So the cable makes some losses between your transmitting to the antenna systems. And after some, so that is with some distance, we have a receiver section. The receiver section is consisting of a receiving antenna and we have a receiver radio part, right? That is the destination part. So in between we have a cable arrangement. So in this communication link, in a wireless communication link, the losses may occur between transmitting radio to these antenna systems due to the cable, as well as from receiving antenna to this reception of these destinations, that is due to the cable, and also between the transmitter antenna to the receiver antenna, since this is a wireless communication channel, and this loss is called as path loss. And see here, this curve is it's telling about with respect to the distance what will be the power distributions in dBm, right? Now see here, this is the green color, all the green color or the power level, that is we can say it is a gain, or all red color lines or losses. So this green color line is the transmitting power. So this is the power which is transmitted by the transmitting antenna, transmitter radio. So now in between the antenna to this transmitter part, we have a cable. Because of the cable, the power has been reduced. So there is a loss. There is a loss. So this slope indicates the power is reduced somewhat. Then because of these antenna, there is a gain we have fixed, right? So the VIRP centimeter effective isotropic radiated power is it's fixed for this antenna. So this is the transmitting power from the antenna systems. So this is the transmitted power we have, and between the antenna transmitter to antenna receiver, there is a loss again. This is due to the path loss. Since it is a wireless communications, we have a path loss. So this power has been reduced to this much. Then again, due to the gain of the antenna, we have this much power we can able to receive. So this is the received power. And again, due to the cable, what is happening? This is the second loss. This is the third loss. So the power is somewhat reduced, and we have received the power almost this much. So now this is the received power, but the receiver sensitivity power is this much. Now this difference between the received power to the receiver sensitivity is called as margin. So that is the margin value, right? So there are the losses between the first transmitter to the transmitting antenna and transmitting antenna to the receiving antenna, and there is a loss between receiving antenna to the station, right? So now we are going to estimate all these gain, transmitting power, loss, everything together to calculate the link budget, right? For example, a 15 dB link margin means, for example, a 15 dB link margin means the system could tolerate an additional 15 dB of attenuation between transmitter and receiver. That means, suppose we want to design a 20 dB receiver, we are going to include 20 dB plus 15 dB, for example, right? Because 15 dB is the tolerate one, right? So 20 plus 15 dB we are going to estimate. So total power will be now 35 dB, right? So 35 dB means we can receive only 20 dB power, because this 15 dB will be tolerable. It will be attenuated, right? So this is the way we are going to calculate. Suppose if the link margin is negative term, what will happen? Now the receiver does not contain any sufficient data. So that is very important factor over here. What is the uses of link margin or link budget? So by assessing link budget, the system can be designed with its requirements. So we can design the entire system in proper way, right? So properly we can design and properly we can estimate what will be the received power, what will be the margin we are going to fix. So how we are going to estimate the attenuation values, what will be the transmission power, what are the losses, all these things we can properly design, then we can estimate the actual received power, right? The link margin depends various factors. The one is transmitting frequency, that also one of the factor, and type of coverage area, and minimum C by N requirement, and nature of obstructions, nature of receptions, type of receiving antenna what we are using, and elevation angle is another factor, and what kind of module systems we are going to use, and the type of delivery system, whether it is a terrestrial or hybrid or satellite. So these are the several factors which may alter the link margin. So link margin depends these factors. So link budget is to estimate the received power, okay, with the help of transmitting power, gain and losses in between. So that is called as link budget. So this is the formula for detailed calculation of the entire cases, including the transmitting power, PTX, and transmitting antenna gain, receiver antenna gain. The LTX is transmitter losses, that is due to coaxial cable or the type of connectors, and LFS is nothing but the path loss, that is usually free space losses, right, that in between transmitter antenna to receiving antenna, where LP is the propagation loss and LRX is nothing but receiver loss, that is the cable connections in between receiving antenna to the destination part. So combining all together the loss factors as well as gain factors and the transmitted power, we can estimate what is the received power by the receiver antenna. So this is called as link budget estimations. So that is, we are going to estimate how much power we can able to receive by concluding all these values. So with this we will wind up the today classes. Thank you.